Okay. So let's start today's session. The first speaker, it's my pleasure to announce the first speaker from Moscow, Ivan Arzhantsev, who will talk about TITS type alternative for automotive groups. Please.
Thank you very much. It's a great pleasure and great honor for me to participate in the conference dedicated to Ivan Arzhantsev. There are already many warm and important words about Ivan Arzhantsev as a prominent mathematician, excellent scientific supervisor, leader of very deep and active scientific school. But I will try to add some words on the opposite side. We saw how productive and open is Ivan Arzhantsev as a collaborator with many researchers all over the world. But here, being a representative of Moscow Mathematical School, I would like to say that the situation changed during the last decade. When I was young, at least from my point of view, the connection between St. Petersburg and Moscow Mathematical School were not so systematic. I remember when I came first time in St. Petersburg, it was a joke that Moscow and Petersburg mathematician meets mostly in billiard. But now the situation really changed. I go to St. Petersburg regularly, as I don't know, not as I go to my office, but quite regularly, almost every month, many joint events, many conferences, schools, and this is very nice. We are very glad to collaborate with our colleagues. And I think that Ivan Arzhantsev is a person who play a key role in this collaboration. And I hope that we will continue.
Thank you. Thank you very much.
Thank
Actually,
you.
GFA had more Russian doctors in algebra than any other Russian university, except Moscow State University.
And now I go to my talk. I will have at the beginning some theory part, and then I will come to our joint result with Michael Zeidenberg and Michael is with us in Zoom, so we might also address the question with him. And this is about TITS alternative. So let me start from the very beginning, from the theorem, which is TITS, dated 72, it's published in Journal of Algebra. I will call this result TITS alternative, T8 for short. I think that many of people in the audience know the result, but let me formulate it precisely. So the first claim is that if the ground field has characteristic 0, then we have the following alternative. Any linear group over K is either which are resolvable this means that this group contains a subgroup of finite index which is solvable. So this is somehow finite extension of a solvable group. Or it contains a free group with two generators. Two generators is not important because you know that if you take a free group with two generators, then its derived subgroup is a free group with countable number of generators. So to contain F2 means to contain F3, F4, and so on. Contains some non-abelian free group. This is a really strong alternative. So either almost solvable or contains such a free object. I yesterday looked to original TITS paper, and TITS wrote that this was a conjecture by Bass and Sev, which he proved. So this appeared even earlier. And if we take arbitrary field for any K, the same holds for finitely generated. So TITS explains that this is wrong in positive characteristic. For any subgroup, he proposed to consider the general linear group over infinite extension of a finite field. Then this result is wrong in this relation. But if you restrict only to finitely generated subgroups, then again, either virtually solvable or contains free subgroup.
May I ask a question? Just, I remember it was a result of Platonov that suppose the group satisfies negativity. Then we have something very, very similar. Is it correct?
Exactly. And it's also written in the introduction of in his paper. He mentioned results of Platonov and says that if it has an identity, then it cannot contain free group, and so this is
So it's virtual.
He also mentioned as this is a motivation for him to do this.
Okay, thank you.
So this is a classical result, and the question is how can we generalize it to other classes? So this result is as old as I am, so it's 50 years old, and for this time people learned a lot about groups with this property or without this property, and I will concentrate on only one possible generalizations. I will speak about polynomial and birational automorphism. So yesterday, in the talk by Oliver Mathieu, it was a question, how similar is the group of polynomial automorphisms to the general linear group? Do they have something in common? And so today I also would like to address this question. So we might consider the, say, automorphic group of a plane as a generalization of GFP. And thus its alternative holds for this group. And it turns out that the answer is yes. This is theorem by Stéphane Lamy, published in 2011 and also in the Journal of Algebra. It's the same place Keith published his result. And the statement is that the group of polynomial automorphism in the complex plane satisfied its alternative. But you may ask which its alternative, because here we have two variants, either for all subgroup or for finitely generated. So in Lanier's paper, there are strong questions for all subgroups. Strong version. And here,
It's important that C is important.
in his paper, maybe yes, because this is claimed only for complex numbers, but now it's proved for any field of characteristics.
So it's complete.
And here the main technical tool is a well-known Jung theorem, not Jung, but Jung under Cook, because we need amalgamated products. There is some structural description of the automorphism. Our group of automorphism is isomorphic to amalgamate product of two subgroups over the intersection, where the first one, A, is the group of affine transformation of our plane. Group B consists of triangular transformation. By this I mean that the first coordinates goes to add some scalar, non-zero scalar x plus any polynomial in y, and for y we have similar things, but we don't have x here, we can add only a scalar. Okay, so such groups may be considered as a group of upper triangular transformations, and C is their intersection. So Jung proved that such transformations generate our group, and Van der Kolk in 53 proved that they have such a canonical presentation. So this is an amalgamated problem, in some sense unique factorization. A, B, A, B, A, B, and so on, modular of the intersection. This is a very strong result, and one can use the theory of action on trees due to CR, and there is some technique to prove that you have this alternative, but maybe this alternative is not the only result. This is somehow a motivation to study the structure of subgroup. And in Lani's paper, we have 4 types of subgroup. Inside of our group. So this is some quite constructive, effective results about subgroups. What can we say about a 3-dimensional affine space? This is open. So we might ask, do we have its alternative for the group of automorphisms of system? As we know, the structure of the automorphism group of affine space is very mysterious. The result of Shostakovich and Mirbayev, which was mentioned, that there is a wild automorphism. This is in some sense negative result. So tame automorphism do not generate. This group contains not only tame but some wild automorphism, and we don't know what is the generating system for this group. So this is quite mysterious. But there are some positive results. First, I would like to mention theorem due to busy for term. And one, this is 2014, and it claims that its alternative in a strong version holds for. Now, I would like to explain what I write. First, let us consider the group SL2, but let us forget for a moment that this is a group. Let us consider this just as a 3-dimensional affine variety. This is smooth variety in affine 4 space. So I look at this as some algebraic variety X. Then we just consider the group of all polynomial automorphisms on this affine 3-dimensional variety. And there is some way to explain what is tame and wild automorphism in this case. Quite actually. I will not now do it, but this is possible. So we consider the group of all tame automorphisms of this affine 3-dimensional variety. And again, its alternative holds here. This result is very important because it was the first result concerning not 2-dimensional but 3-dimensional. But very recently, it was a theorem by Lani and Zipsky. Correctly, and this is published in June this year. It appeared on Archive, and it claims that again its alternative in its strong version holds for only tame automorphisms of affine 3 space, where our ground field is any field of characteristic 0. Yes, you're right. So this is a very strong result. This is quite long paper, 60 pages, and this is very important result. It's not published. Okay. So these were some results about polynomial problems. But what is more surprising that we can prove its alternative even in
change the black box.
Sorry?
You can change the black box.
I see.
Basically, shift up.
My problem is that I'm very tall and it will be difficult for me to. So maybe to do like this. Okay, and so maybe the last theorem which I would like to mention in this survey part. This is theorem due to compound. This is 2011, and 10 years later, published one more paper by Ulrich, and it claims that the group of birational automorphisms C2, or in other words, the second Cremona group, satisfies its alternative. As to my intuition, this is really unexpected because it's a group of birational automorphisms in the field. It's a really huge, but nevertheless, and it's not similar to the general. But nevertheless, we again have this result of this alternative. You may ask how it's possible to prove one theorem in set its differences 10 years, but here it was proved for finitely generated subgroups. And here the proof is strong. There was one type of groups which were not clear how to do this, and they are not finitely generated, but they were studied in this paper. Proof in complete generation. So these are results which are known. There are many other results, but I mentioned just a bit of them. There are descriptions of concrete types of subgroups and so on. But this is only the beginning of a general picture for its alternative for automorphism. And now I would like to come to our results. This will be my section 3. This will be T type alternative. For special first, I should explain what I mean. What does it mean, T type? Its type means that its alternative holds for all groups of some class, but no subgroups. So what do you mean? You take some class of group and prove that for any group of this from this class, you either have virtual solvability or it contains a free group of non-commutative free group. But we don't consider subgroups. So in some sense, such results are weaker, but nevertheless, if this class is quite rich, then this may be interesting results. So this is what we are going to do. And what do I mean by special groups? Here I need to have some recall from algebraic group theory. So from now on, I assume that my field K has characteristic 0, and this is algebraically closed. So no positive characteristic, no arithmetic. I will stay in this classical settings. Now I come to a crucial point. I should try to erase.
How crucial is the dimension? What is so that means so we have to consider plane or
if you take, say, phosphorus, then the structure of the automorphic group is even. The class of automorphic group of 4-dimensional space is even more mysterious, because in this case we don't know, do we have valid automorphism or not. Shestakovo-Mirvaev group works only for 3 dimensions.
So the example works for 3-dimensional, case.
Yes, so there is some specific of this case, and as far as I understand, there is no technique.
So okay, good. Clear, thank you.
Okay, so either I will be lucky or talk will stop, but let me try to erase. When it's that, then it's not possible to continue. So at this point, I need some basic facts to see what in the algebra. Namely, I would like to recall the following thing. So if we have a G, which is linear, algebraic, and let me assume connected over my nice field of characteristic 0, algebraically closed, then there is a basic structure theorem that any such group is an almost semi-direct product of some semi-simple group and solvable radical. They may have finite intersection. This is a normal subgroup. This is not normal in general, but we always have such a decomposition. And there is one more decomposition. Namely, we may take maximal reductive subgroup, and then it will be honest semi-direct product with the unipotent radical. Maximal normal unipotence. So we can use either this or this. And we would like to consider additive group of my field. I will denote it by GA. This is just one-dimensional unipotent group, which may be realized by matrices 2 by 2, but this is just the additive group of my field. And now there is a lemma, which I learned from a paper by Vladimir Popov, that the following conditions are equivalent. My linear algebraic group G is generated by GA subgroups. If and only if this group has no characters, so the group of characters is trivial, this group doesn't admit any homomorphism to the multiplicator. And one more equivalent condition is that this decomposition is the following. We should take the first part from the first decomposition and the second part from the second. So this is just the semi-direct product of some semi-simple and unipotent. So what is excluded? Excluded in the central torus in the reductive part. Something like in GRN, we have a one-dimensional central torus. So this is not allowed.
You assume something on the field.
Algebraically closed and of characteristics. Yes, so the second idea.
For the second part,
Mhm.
to be generated by.
Let us stop a bit on this because this is important. If you take any linear algebra, this is always generated by one-dimensional subgroups. But which one-dimensional subgroups do we have? We have either additive or multiple. There are just two one-dimensional connected linear algebra. So I don't want to use multiplicative. I use only additive. People who are not in this business, they may expect that then we will obtain only unipotent. Definitely not. We may obtain some simple groups, say SL2 generated by additive groups. And the class of group which we really can obtain here is of this form. Okay? And so let us try to apply its alternative for this class of group. So it follows that G is unipotent, or G contains F. So its alternative in this case is a bit better, because we don't need virtually solvable, we simplify it to unipotent. Because either this group is unipotent, or it contains non-trivial semi-simple part. Non-trivial semi-simple part means it contains either SL2 or PSL2, so it contains free non-abelian figure. Okay, so this is quite obvious from the classical algebraic C. And now we want to generalize it to infinite dimensional case. Generalization will be the following. I consider not necessarily linear, but some actions of my additive group of the ground field, my GA subgroups, on some algebraic varieties. So this is the algebraic variety. I consider regular linear, some regular action. In this case, I obtain GA subgroups in the automorphism. So if I have a regular action of the additive group of the field, then it gives me some subgroup inside of the group of automorphisms of my variety, and I call this GA. Okay. So our main conjecture is the following. If X is affine, And if G is generated by finitely many such GA subgroups, then either G is unipotent or G contains F. So this is its type alternative. We are not interested in subgroups of these groups, but we allow, this is quite wide class of subgroups of the group of automorphism, which is generated by finitely many additive groups. It includes groups of this form, but we have many finite infinite dimensions. And we claim that we still have this specific version of the its alternative. I still say I have some time, so I would like firstly to say some motivation. Why, how this conjecture appeared to us. The idea was to use one bread, but this is not so funny. Much more funny is to try to
Actually, there is another.
what was our original problem? It was the following. So, original motivation. We studied some properties of actions of automorphism groups on a fine variety. Namely, let me take some abstract group, not necessarily algebraic. And let me take some set. And let me take an action of this abstract group in this abstract set. You know what is transitive action, when we any point can move to any point. And in this case, we consider stronger condition. We say that this action is infinitely transitive. For any positive integer present, G is transitive on M tiles. In X. So our group not only moves any point to any point, but any pair of different points to any pair of different points, and a triple of different points to a triple of different points. So the action is as transitive as possible. Certainly we may define what we want, but does it happen or not? But it happens. This is quite easy to prove that the group of polynomial automorphisms of a affine space, starting from dimension 2, is infinitely transitive. And it turns out that infinite transitivity is quite usually the case. So if you consider the group of, we call it S out, this is the group generated by all GA subgroups. So I take some variety, I take its automorphism group, I take all GA actions from this variety, so I take all GA subgroups in this automorphism group, and I generate, no topology, no closure, I generate as an F subgroup, this group S out. These are elements which are products of elements from some GA subgroups. This is normal subgroup in the automorphism group. And let me say sometimes, and even often, this group is infinitely transitive on X. Certainly, it is transitive, that is a variety smooth, this is clear. But for smooth variety, especially for affine, but even for quasi-affine, we have many examples. This theory is called theory of flexible varieties. Varieties with this property are called flexible. Homogeneous spaces of simple group which are affine or quasi-affine they have this property. So this is quite rich class of algebraic parameters. But here I took all GA subgroups. Usually there are many GA subgroups, and this group is very big. But you may take only finitely many a subgroup, but it may happen that the group G generated by finitely many GA subgroups is infinitely transitive. And for us, it was really a surprise when we realized that this is possible. Because what is the reason for the infinite transitivity? We have some notion of replicas, we can stop point here, move point there, there is something, but it doesn't work in the case when the group is generated by finite dimensions. So what does it mean that you have just finite dimensions? You may move in this direction, this direction, this direction, finite directions. And applying only this transformation, you should move any m couple to any m couple. Looks impossible. But nevertheless, it's possible. And I would like to present just one example. Very simple, with a affine plane. Example. Let us take a affine plane and take just two GA subgroups. The first one, I will denote it UA, will consist of the transformations of the following form: x plus alpha y power a y, where alpha is some scalar, some elements of my additive, of my field. So this is parameter in my one parameters. I add a's power of the first coordinate, of the second coordinate in the first coordinate. Okay, one concrete GA. And the other one, UV, or the similar one. Here, x is fixed, and we have y plus beta x, and beta is again, and a and b some fixed positive integers. So theorem say that if we take a group G, which is generated by only these two subgroups, UA and UB, it acts on the affine plane, but honestly speaking, it's not possible to be transitive, because if A and B are non-negative, then they fix 0 point. So we should remove 0 points from here. So it acts on the plane without 1 point, infinitely transitively. If and only if, and it was a very big surprise. Because what one may expect? Never. Just two transformations, so no chance to this. Or for sufficiently big A, or almost all, something like this. And the answer was very strange for us. The answer is if and only if AB equals maybe some guess. 1, 2, or 2, 1. One side linear, other side quadratic. 2 quadratic, no. 2 linear, definitely no, because they generate the SL2 and this is finite dimension. 2 cubes, I don't know. In all other cases, we have, we don't have two transitivity. But only for this strange case, linear and quadratic, I don't know why, but we have infinite.
So how this is very closely related to teach them.
Yes, this is fine. This is my motivation to go to this. And I will not list all who prove it, because this was partially proved by us. We conjectured the second part, and it was proved in the paper of our American colleagues. So there's a long list of people to contribute to this, but nevertheless, this is true. And after this, we start to think maybe there is some group theoretical reasons why in some cases we have infinite transitivity, in some cases not. Maybe this is related to growth of subgroup, something like containing free subgroup, not containing free subgroup. So, and that is why we start to think about different.
Of course, alpha and beta are not zero.
Alpha and beta may be zero because they are parameters in our additive group.
These are
This is the ground group.
Yes,
This is the ground group of additive group of the ground field. Okay, and this conjecture, it shows that no, infinite transitivity is not connected with this alternative somehow, because we have either free subgroup, and then we don't know, maybe infinite transitive, maybe not, or unipotent. If it is unipotent, then it's finite dimensional, it cannot be even two. But it was motivation in some sense negative result, but I now would like to formulate positive. Still sometimes. But I would like to address to young participants of this conference. You will go in vitro and you will have time. Please think. You have just two types of transformations. You can add linear y to the first coordinate or square of x to the second coordinate. And you should move any triple of point to any triple of points. Please try. Don't trivial. Okay. So I come to results. Theorem 1. So our paper, as Mr. Grigorich says that if X is a fine additionally toric, and if our group G is generated by finitely many GA subgroups, but they are not arbitrary, they are root subgroups. I will explain what it means. Root GA subgroups. What is a toric variety? This is, in my case, a fine variety with a given action of an algebraic torus. And this torus acts with an open orbit. So I have a torus as an open subset in my variety, then something on the bound. And torus acts not only on himself in this open orbit, but on the whole variety. And if I have some subgroups in the automorphism group, then they may be compatible or not with this torus. By compatible, I mean that this torus normalizes subgroups. So root subgroups means that these GA subgroups are normalized by this maximal torus in the automorphism.
And minimal such.
No, they are one dimension. So torus acts by some character. Say if you take SLN, this is not toric variety, but in any case, you have some maximal torus, and subgroups which are normalized by maximal torus are just one-dimensional subgroup corresponding to elementary matrices. So this is like usual variant of this one-dimensional elementary subgroups. Okay. There is some beautiful theorem due to Di-Mazur originally. Di-Mazur considered complete case, but it may be quite easily generalized to the following case. Some combinatorial description of such root subgroups. They are classified by so-called Di-Mazur roots. If you have a sign of your variety, this is some picture, you add some other pictures, and you obtain some combinatorials which describe all such things. For complete toric varieties, the number of roots is always finite. For a finite toric varieties, the number of roots is starting from dimension 2. But we take only finitely many root subgroups. And then we claim that our conjecture is true. G is unipotent, or G contains. And in this case, we have some technique to do this. We apply some methods from Lie algebras. The roots may be considered as infinite-dimensional generators. They correspond to some characters, and we can apply some Lie algebras. So we can prove it here. And our second result deals with two-dimensional. X is a finite circle. And here G is arbitrary subgroup generated by finitely many GA subgroups. No restrictions like root, nothing like this. Any GA subgroup, so in complete generality, then we claim that G is unipotent. And in this case, we even can add metabelian. Or G contains. So this is even a stronger alternative. But this stronger alternative might produce some doubts. So maybe surface case, just two-dimensional variety, so simple. Maybe there are no GA action or almost no GA action. And maybe here the situation is somehow trivial. No, the situation is not trivial, and I would like to give two examples which show that the second result is not trivial. Example number one. This is the case when I take not the automorphism. Here, these are subgroups in the automorphism. But I would like to consider the Cremona. In Cremona 2, our conjecture is wrong. So we don't have simple. Very easy example. We take the first group is just parallel translation along the first coordinate. I add some scalar to x. And the second, here we have some rational, not regular function. First coordinate is fixed, and second coordinate is y plus beta over x. And again, alpha beta arbitrary stuff. So something like in our previous case, but here we add not x, but x inverse by rational transformation.
K2.
Yes, this is a group of. This two means that over the field I have birational automorphism of their function.
Of plane?
Plane. This K is for field, and this 2 is for K2.
Oh.
So this is the second Cremona group. So this is a group of birational transformation. And you can easily see that if you generate a group by these two subgroups, but then what you obtain, this will be something inside of the group of the following form, x plus scalar and y plus some rational function of x. And this group is metabelian. So our group is metabelian, but this is not unipotent in the usual sense. Unipotent means finite dimension, but this group will be so our alternative is somehow strong. Either finite dimensional unipotent or contains. We don't have infinite dimensional, but for Cremona you might have infinite dimensional. Certainly, it's not contradictory to its alternative because this is very soft. This is not good. And maybe one more example, maybe here. Non-trivial actions on affine surface. Example number 2. for any positive integer m, we may consider the following. We may consider the group of regular polynomial automorphism of the following form: x plus alpha and y plus gx, where I restrict the degree of polynomial g. Degree of g is at most m. And this is some finite dimensional subgroup unipotent. It acts on my plane K2 effectively. It acts transitively. And its dimension, this is a polynomial of degree at most n, so we have m plus 1 coordinates plus this alpha, so dimension is n plus. And this is again somehow difficult to accept, because consider a fine plane, which group may act on a fine plane? At most 2 dimensions, or no, at most 3 dimensions, because SL2 can act on a fine plane. But no, there can be action of a group of arbitrary dimensions, and this action will be effective, so no kernels. And so, and this is an example. And this action acts transitively, and we may construct as big unipotent group as we like. And you can say even more. We can omit this alpha. If you omit this alpha and say that x is fixed, then our group will be computed. And there will be no more open orbit, because x is fixed. It means that some levels are fixed. So generic orbits are one-dimensional. And again, group may have as large dimension as you want, and the action is unbelievable. So 2-dimensional plane, 1-dimensional orbit, very, very big group acts with this 1-dimensional orbit and no kernel.
That seems to be lines. The orbits are lines. Yes?
Or orbits are lines. And the reason is that the stabilizer changed from orbit to orbit. So you have your huge group, it has very different stabilizers, and the intersection of the stabilizers is trivial. So the action. So these are examples that unipotent group may act on defined surfaces in quite non-trivial. So our result in this sense is non-trivial. We may this and that. But if group is generated by finitely many J subgroups, then either unipotent or contains. So this is it. So thank you very much for your attention.
Any questions, remarks?
Once again, who finally generated, repeat please. Who finally generated case?
But here I should stress, I don't consider finitely generated in the terms of usual group theory, when it is generated by finitely many elements. Because we consider algebraic group, no chance, because this is only for discrete. But finitely generated, I mean generated by finitely many GA subgroups. And GA subgroups, this is my ground field, so this is for fields of complex number uncountable. But this is as the group SLN. Group SLN, as we know from work of Nikolai's school, is generated, and we may, I don't know, restrict the number, write explicit expressions about this nice generated by elementary groups. So this is some attempt to do something like this in infinite dimension.
The question was about model theory. If you take such a group in this sense, as you said, and take an elementary equivalent to it, what can be said about this group?
About model. Model theory.
Yeah, should. There's a result, well-known result of Marxov, that if you take a linear finitely generated, so to say, and then take another elementary equivalent, also will be linear.
No, but Jenny, these are finally generated by subgroups, not by elements.
Yes, that was the
That's
question.
exactly the.
That was the question. So in this sense, what does it mean? Not, it's not an immediate question.
Yes, it's interesting to think, but let me share again my own impression. When you start, when you're a student of, I don't know, third year, and you start to study theory of algebraic groups. Firstly, you know that there are some unipotent or solvable groups. And you know some Lee-Colchin theorem, Lee theorem, that they can be written by unipotent upper triangular or, in solvable case, any upper triangular methods. And this is all. And usually in textbook, people stop here with solvable groups and come to beautiful theory of semi-simple. And for semi-simple groups, we know almost everything. All representations are completely reducible. There is a highest rise theory and this and that. But when you start to work with this, you realize that something is missing because any group is a combination of reductive and unipotent. About reductive, you know everything. About unipotent, you go to the beginning of this textbook. It was some elementary theorem like Lee-Colchin, and what else? And almost nothing is known. What is a representation theory of unipotent groups? Okay, this can be made upper triangular with units on diagonal, but say more. And it turned out that this is a difficult violence problem. And say geometric invariant theory, take coefficients, take Mumford variant of the semi-stability. This is pretty well done for reductive groups. Try to do it for arbitrary groups, say for unipotent. There are many attempts, but no canonical theory. And this is interesting to study unipotent groups and unipotent elements.
But my question was about, it's well known if you take ultra product, ultra power of a linear group, it will be interesting. Now, in your object, it's something very similar. And so we have automorphism group polynomial. What will happen? That's a question about a model theory of such group. How rigid are these groups in respect to elementary recurrence? I'm sorry.
I see.
Okay, other questions, remarks?
Well, I'm most impressed by the amendment because it's really unexpected that you have the same kind of answer, well, with the same kind of explicit answer as Titzlem and Bashkirov lemma for generation and cyclinear groups. Here, these are huge infinite dimensional things. You have the same. This means that there might be a geometry with a completely different direction from what Jenny asks, that there might be a combinatorial geometry of the same type as geometry of fruit subgroups in the limit. Which we do not see because it's completely different kind, different dimensions. But that's a side of the
So let's thank this group.